Okay, so for this question, this was question 4 in 2009, we have this region R, and so what we're going to do is take a second and draw that. We've got an X and a Y. We've got the linear function y equals 2x, and we've got the quadratic y equals x squared. So we'll let this be 4, halfway be 2, 3 and 1, and so then, oh, well, yeah, okay. At 2 it should be 1, or at 1 it should be 2. And then that's not horizontal. That's less horizontal. Okay. And then at 2. Okay, so we've got the quadratic x squared that looks like this. So okay. In part A, it says find the area. The area of the region R, where R is this space in between them. Okay? So let's just remember that area is just the area between the two curves. You have two different options. You can do the integral. You can do vertical strips if you go down the x-axis, and so that would be a top minus bottom situation, so it would be 2x minus x squared dx. No squares or anything, like we're not squaring the whole thing, this is not revolution. And then we would go from 0 to 2. So that's one way option. Or we can do right minus left, and in which case we're going up the y-axis, so horizontal strips up the y. So that would be the integral from 0 to 4. The right-hand function would be this one, so it would be the square root of y minus, and then y divided by 2. But either way, it would get you the same answer. So we should get x squared minus x cubed over 3, evaluated from 0 to 2. So that would be 4 minus 8 thirds, and then minus 0. And 4 is 12 thirds, so 12 thirds minus 8 thirds is 4 thirds. Okay, if we antiderive this one, you don't have to do it both ways, I'm just showing you. This would be y to the 1/2, so add 1 to the power, 3/2 times 2 thirds, minus, add 1 to the power, divide by the new power, from 0 to 4. So we're going to plug in 4. The square root of 4 is 2, 2 cubed is 8, 8 times 2 thirds is 16 thirds, minus, and then 4 squared is 16 divided by 4, that's 4, and 4 is 12 thirds. So we get 4 thirds either way. Okay, so that's part A. Part B says the region R is the base of a solid. For this solid at each x, the cross-section perpendicular to the x-axis has area given by this. So we're talking about cross-sections, but notice how it's not one of the ones that we like learned. It's just a general, it's a function. The area is modeled by sine of pi over 2x. Find the volume of the solid. So just as a reminder, volume is the integral of area. So in part B, if they're telling me the area of the cross-sections is modeled by a of x equals sine of pi over 2x, and the cross-sections are perpendicular to the x-axis, yeah? Perpendicular to the x-axis, that means my cross-sections are vertical, okay? But I don't actually have to worry about these functions, okay? These functions don't play a part in figuring out the volume because all I have to use is the area formula. The only thing that this cross-section being perpendicular to the x-axis is necessary for me to do in order to do this problem is to know to go from 0 to 2 and not 0 to 4. So this is the integral from 0 to 2 of sine of pi over 2x dx. Now, as far as anti-deriving this, this is a u substitution because it's not just sine of x, it's sine of pi over 2x. So u equals pi over 2x, du equals pi over 2 dx. We don't have a pi over 2 out front, so we put 2 over pi. The integral from, well, let's just say sine of u du. And I'll go ahead and change my limits of integration here. So plug in 0 and I get 0. Plug in 2 and I get pi. Okay? So we antiderive sine and we get negative cosine, so negative 2 over pi cosine of, we'll go ahead and say u, evaluated from 0 to pi. So this is one of the situations where you can't discard 0 because it's not a polynomial, and it's cosine. So I'm going to put negative 2 over pi outside, cosine pi minus cosine 0, or you could have distributed the negative 2 over pi to each of them, and either way we get negative 1 minus 1, right? So cosine of pi is negative 1, and cosine of 0 is 1, so that's negative 2. So negative 2 over pi times negative 2, or 4 over pi. There you go. And as you can see, that is what they did as well. So they're looking for the integrand. The integrand is the thing inside, the antiderivative, what you got, and then your answer. Okay. So let's talk about part C. Another solid has the same base. For this solid, the cross-sections perpendicular to the y-axis are squares, right, but do not evaluate an integral expression for the volume of the solid. So what we have in this situation, so for part C, we have cross-sections perpendicular to the y-axis are squares. So as far as remembering the formula, squares is just the base squared. So we've got this, and then we got this square, right? Pretend like that's a square. The area formula for a square is base times height, and like we said, you know, in all our formula, squares was the integral of f of x squared, where f of x represented the base length. That could be top minus bottom, right minus left, whatever. But in this case, it's just right minus left, so it's going to be, again, the square root of y on the right-hand side and y divided by 2 on the left. So it's going to be the integral. Now these are horizontal cross-sections, so they go up from 0 to 4, of right minus left, so square root of y minus y over 2, quantity squared, so that's the difference between that and this and area, dy, and remember squares is the only one that doesn't have a coefficient. So just a reminder, rectangular has a k, rectangular cross-section has a k out front, some constant variation. Not constant variation, but constant scalar. Semicircles has pi over 8. Equilateral triangles have square root of 3 over 4. And isosceles right triangles with the leg in the base is 1/2 and hypotenuse in the base is 1/4. As we said, we have 2 legs and hippopotamuses have 4. Okay, and that's it for that one. Pretty sure that's all they needed, so we're good. 2 whole points for that integrand, right? And then 1 point for the Lorentz integration. Not that you're going to have that same kind of situation going on, but you know. Okay. Here goes question 4 for the BC test. So you guys had very similar, not very similar, you had some of the same questions, but then question 4 and question 6 for BC were completely different. So, consider the differential equation. Okay, so let's go ahead and write that down. dy dx equals 6x squared minus x squared y. Let y equal f of x be a particular solution to this differential equation with the initial condition f of negative 1 equals 2. Let me go ahead and write differential equation, and you should too, just like a reminder to yourself, like the type of problem you're dealing with, to start off with. So A, use Euler's method with 2 steps of equal size starting at negative 1 to approximate f of 0. Okay. I don't like how I did that, but oh well, whatever. Okay, use 2 steps of equal size, so that means negative 1/2, which means the change in x is, I think we're going to go ahead and say the change in x is 1/2 because we're going forward 1/2. Yeah, I think so. Say delta x equals 1/2. Okay, so remember we got the x, we got the y, we got the dy dx, and then we got the dy, and we figure that out by multiplying by the change in x dx. Okay? So, at negative 1, y is negative or positive 2, because it gave us that, right? Okay, so our goal is to approximate f of 0. Our goal is this answer right here, whatever is in this box. Okay, so we're going to plug these two into our derivative. I'm a fan of making the derivatives as easy as possible to substitute in, so I'm going to factor out an x squared. Okay, so I'm going to plug in x as -1, that's just 1. And then 6 minus 2, that's 4. Okay, I'm going to multiply that by the change in x, which is 1/2. So that's 2. And then that's the change in y, so we're going to add that to that, so we get 4. Okay, now I'm going to multiply, or I'm going to plug in x is -1/2, so -1/2 squared is 1/4. And then y is 4, so 6 minus 4 is 2, so that's going to be 1/2. We're going to multiply that times the change in x, that's going to be 1/4, and we're going to add that to 4. So 4 and 1/4, or 17/4. Let's make sure that we are correct. And we are. Okay. So we need to make a statement f of 0 is approximately 17/4 using Euler's method. Okay. Part B. At the point -1, 2, the value of the second derivative is -12. Find the second degree Taylor polynomial for f about x equals 1. Okay. So at -1, 2, the second derivative equals -12. We need the second degree Taylor polynomial. Okay, about x equals -1. Alright, so let's remind ourselves. We've got 1 plus, then we do, oh, sorry. I don't know why I said 1. We've been doing some other problems first. So we do f of -1. I believe first, don't we do that? Like f, yeah. Let me make sure. Yeah. Okay. Plus f prime, sorry, brain fart, times x plus 1, because it's centered at -1, plus f double prime at -1 divided by 2 factorial times x plus 1 quantity squared. The next term would be f triple prime at -1 divided by 3 factorial times x plus 1 cubed. But we only need the second degree Taylor polynomial. So f of -1 is 2. F prime at -1, we said f prime at -1 was 4. The derivative was 4 times x plus 1. And the second derivative is -12. So minus 12 divided by 2 factorial, which is 2, or just 6, times x plus 1 quantity squared. So let's make sure we're correct. And just so you can see, it's 2 plus 4 times x plus 1 minus 6 times x plus 1 quantity squared. Perfect. Okay. Then part C, it says, find the particular solution to the given differential equation with the initial condition f -1 equals 2. So this is actually just solve the differential equation. Okay, let me do that. So I'm going to go back to the beginning where I've got the derivative. dy dx equals 6x squared minus x squared y. And if you remember, I told you that the first step in solving a differential equation, if it is separable, is to separate the variables. We haven't really talked about any other way to do it. So I need to get x's on this side and y's on this side. So I cannot add this over. Just don't forget, you can only use multiplication and division. So we're going to go ahead and do what I did here where I factored it out. X squared times 6 minus y. And then we're going to divide by 6 minus y, so 1 over 6 minus y dy equals x squared dx, and then we're going to integrate. Okay? So this side is easy, x cubed over 3 plus c. This side, you have to remember that this is technically a u sub. I mean, you've got 6 minus y being raised to the first power, so if you try to bring it up as a quantity and you add 1 to the power, you get 0. So that should trigger your memory like natural log to be thinking about that, but it's 6 minus y. So technically that requires a u sub. U equals 6 minus y. Du, the derivative of that, is -1 dy. We don't have a -1, so it's negative the integral of 1 over u du, which is negative natural log of the absolute value of u. So negative natural log of the absolute value of 6 minus y equals x cubed over 3 plus c. Personally, I like to solve for c right now using the initial condition, f of negative 1 equals 2. So we're going to plug in a 2 right there, so negative natural log of 4 equals, when I plug in negative 1, I get negative 1/3. So then we get c equals so c is going to be, if I add the 1/3 over, I'm going to go ahead and, I'm going to go ahead and put it like this. Negative natural log of 4 plus 1/3. So if I add the 1/3 over, then that's what c equals. Alright, so now we're ready to do the last part of this, solving the differential, which is solving for y. So the big key points are, separate the variables, don't forget c, solve for c, now solve for y. Okay? So we're going to divide by negative, natural log of the absolute value of 6 minus y. So it's going to be negative x cubed over 3 plus natural log of 4 minus 1/3. We're going to undo the natural log, so we're going to raise both sides to the power of e. So the absolute value of 6 minus y equals... Now, this right here, you can just leave it. There's nothing wrong with that, okay? But if you want to be able to simplify that, you could split it up and say it's e to this. You could split up the natural log of 4 from this and separate them a little bit. So you could say it's e to the negative x cubed over 3 minus 1/3 times e to the natural log of 4, which is just 4. So it's 4e to the negative x cubed over 3 minus 1/3. And then if you want to get rid of the absolute value bars, you put plus and minus. Right? If you're going to move the 6 over, we're going to subtract the 6 over, and then we're going to divide by the negative. So, give me a second. So negative y equals negative 6 plus or minus 4e to the negative x cubed over 3 minus 1/3. And then, getting rid of the negative becomes 6. This becomes minus plus, who really cares? So 4e to the negative x cubed over 3 minus 1/3. Remember that our initial condition is that when you plug in negative 1, you should get 2. So if I plug in negative 1 right here, this becomes a positive 1/3. And a positive 1/3 minus 1/3 is 0. E to the 0 is 1. The only way that I'm going to get 2 is if it's 6 minus 4. So 6 minus 4e to the negative x cubed over 3 minus 1/3. Okay. So you can read that. Okay. And that is the question 4 from the BC. Let's see. We didn't have any natural domain issues because it was just this polynomial, or, well, definitely not a polynomial. It was just this algebraic expression. It didn't really say anything about it. A lot of times when it's situational for the differential equation, you can use that the situation to figure out your domain. But anyway, that is what they have. So we're good. All right, last 2009 question. So we've got the Maclaurin series for e to the x is e to the x. Let's go ahead and write that down. Okay, so everyone write down e to the x equals 1 plus x squared over 2 plus x cubed over 6 plus ... plus x to the n over n factorial plus ... Okay. The continuous function f is defined by this. So f of x equals e to the x minus 1 quantity squared minus 1 all over x minus 1 quantity squared. For x not equal to 1, and then f of 1 equals 1. The function f has derivatives of all orders at x equals 1. Okay? Part A says, write the first 4 non-zero terms and the general term of the Taylor series for e to the x minus 1 quantity squared. So if e to the x equals this, then e to the x minus 1 quantity squared is going to equal. So all we're going to, first 4 non-zero terms, right? So what we're going to do is we're going to just plug in x minus 1 for every x minus 1 quantity squared. So we've got 1 plus x minus 1 quantity squared plus x minus 1 quantity, now it's squared, so to the 4th, divided by 2, plus x minus 1 squared to the 3rd, so 6 over 6. And then, yeah, plus dot 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 plus, and then we've got x minus 1 squared to the nth power, so the 2nth over n factorial plus. Okay. So now let's talk about Part B. Use the Taylor series found in Part A to write the first 4 non-zero terms in the general term of the Taylor series of f about x equals 1. Okay, so this one's going to be a little bit more interesting. It's going to take a little bit more work. Okay. So f of x equals this e to the x minus 1 quantity squared minus 1. And then we're going to have to divide by x minus 1 quantity squared. So here's how we're going to do this, okay? First off, if I take this function, I'm going to kind of discard the general term, and we'll deal with that in a little bit. Or finding the general term, or new one anyway. And I'm going to subtract 1, okay? So if I take this and I subtract 1, then that 1 goes away. So we're dealing with this, right? But then I have to divide this by this, yeah? So you can see how, I was working on it using, yeah, we are still going to do it. Okay. It's very tempting to just be like, oh, let me divide every term by that. But we are actually going to have to work it out using long division. I'll show you how. Okay. So if I take this and I subtract 1, I'm left with x minus 1 quantity squared plus x minus 1 to the 4th over 2 plus x minus 1 to the 6th over 6. Now what I'm going to need to do is go ahead and keep going because I need 4 non-zero terms, which means I need 1 more for this portion of the problem, of our answer anyway. So you can see the pattern, you're going up in even powers. So x minus 1 to the 8th, and then these are the factorials. So 1, 2 factorial, 3 factorial, 4 factorial, which is 24. Okay. So it's important that when you do these Taylor polynomials, you don't just think, oh, I can just, divide by this and just divide every term. I am going to actually have to do long division by x minus 1 quantity squared. Okay. So, well, maybe we can. Oh, yeah, we can. Well, that's silly. Yeah, literally. Yeah. Okay. Sorry, I was thinking that the denominators were offered a little bit differently. I'm going to start working it out this way because I want to show you that you can use long division with these, but we could just divide. That's smarter. Okay, so if I were, what do I need to multiply this by to get that? It's just 1, and I get x minus 1 quantity squared. Subtract, and they're gone. What do I need to multiply this by to get that? And that is x minus 1 quantity squared divided by 2. And then you multiply that and you get the same thing. And they go away. And then what do I need to multiply this by to get that? And that is x minus 1 to the 4th over 6. Yeah? So if I multiply this times this, I get x minus 1 to the 6th over 6. Subtract, and those go away. And obviously I should be going down, but no, whatever. They don't actually have, multiple terms, it's just the one term, so we're good to just keep on going. And then one more, we've got, what do I need to multiply this by to get that? And that would be x minus 1 to the 6th over 24. So I could have just taken this right here and just divided it every term by x minus 1 quantity squared. Okay. I don't know why I made it a long division problem, but you can do long division with them. Okay, so here's what I've got. So, just a reminder, we took e to the x minus 1, which was just e to the x, and then we replaced x with x minus 1 quantity squared. I subtracted 1, which meant that term went away. And then I only had 3 terms that were non-zero, so I had to tack on one more term, this one. And then we just divided each of those by x minus 1 quantity squared, which means I could have just said divided by x minus 1 squared. Okay? So, could have made it a lot easier than doing this, but whatever. I did it. So we get 1 plus x minus 1 quantity squared over 2 plus x minus 1 to the 4th over 6th plus x minus 1 to the 6th over 24. And then we're supposed to come up with the general term, right? So what we're going to do is we're just going to take this and just see about what's going on, okay? So if this is a 0, 1, 2, 3, we can see that it's x minus 1 to the double of the number of terms, so x minus 1 to the 2n, right? Divided by, and it looks like the denominator is just, so this is 1, this is 2 factorial, this is 2, this is 3 factorial, this is 3, this is 4 factorial. So it's the n plus 1 factorial in the denominator. And then plus da da da. Okay. Alright. Let's read about part C. Part C says, use the ratio test to find the interval of convergence for the Taylor series found in part B. Okay, so let's just remind ourselves of the ratio test real quick. The ratio test is where you have the sum of a series, or a series converges absolutely when the limit as n approaches infinity of the nth plus 1 term divided by the nth term, the absolute value of that is less than 1. It diverges when that limit is greater than 1 or going to infinity, and it's inconclusive when the limit equals 1. Okay? So, we'll keep that in mind. And we'll do the ratio test. Okay, so we're going to do, found in part A. Use the ratio test. Use found in part B. Okay. So A sub n equaled x minus 1 to the 2n over n plus 1 factorial. Now, if you'd gotten the general term wrong, then you would have just used whatever you had come up with, and then you would have just gone with it. Okay? So, we're going to take the limit as n approaches infinity of the absolute value, and we're going to do the nth plus 1 term divided by the nth term. So the nth plus 1 is going to be x minus 1 to the 2 times n plus 1, or 2n plus 2, divided by n plus 1 plus 1, so n plus 2 factorial, divided by, I tend to like to go ahead and do the multiplication, but I'm just going to go ahead and do this. X minus 1 to the 2n over n plus 1 factorial. Okay. So let's go ahead and do that multiplication. So limit as n approaches infinity of the absolute value, x minus 1 to the 2n plus 2 over n plus 2 factorial times n plus 1 factorial over x minus 1 to the 2n. Okay. So remember, n is the variable, not x, okay? So if we think about this is x minus 1 to the 2n times x minus 1 quantity squared, because when you have the same base and you multiply them, you add the powers. Which means this and this can go away. And then n plus 2 factorial is just n plus 2 times n plus 1 factorial. So as you go down in numbers, so n plus 1 goes away. So we're taking the limit as n approaches infinity of x minus 1 quantity squared over n plus 2 factorial. So the only n I see is, not factorial, just n plus 2. The only n I see is in the denominator, which means this is going to 0, which is less than 1. Therefore, this always converges. So the radius, or the interval of convergence, did I say radius or interval? This is interval. Interval of convergence is negative infinity to infinity. Okay, if they ask for radius, then I would say the radius is infinity. Okay, let's talk about part D. Use the Taylor series for f about x equals 1 to determine whether the graph of f has any points of inflection. Okay, so use the Taylor series for f about x equals 1 to determine whether the graph has any points of inflection. So, we're going to find the first and then the second derivative of f, with f being this thing down here. Okay? Yeah. Okay. Because f of x was this one right here. So if this is f of x, let's find f prime. Okay, so f prime of x equals, if I bring that down, I get 2 times x minus 1 over 2 plus 4 times x minus 1 cubed over 6 plus 6 times x minus 1 to the 5th over 24. I don't know if I want to keep on. Let me do yeah. 2n times x minus 1 to the 2n minus 1 over n plus 1 factorial. Okay, let's find the second derivative. So this is a power of 1. If I bring that down, then this becomes x minus 1 to the 0 power. So this just kind of goes away. Should I have f of x or f of f? Yeah, we're good. Okay. So raised to the 0 power, that just becomes 1. Plus, if I bring the 3 down, this becomes 4 times 3 times x minus 1 squared over 6 plus 6 times 5x minus 1 to the 4th over 24 plus 2n, bring the power down, 2n minus 1 times x minus 1 to the 2n minus 2 all over n plus 1 factorial. Okay, so let me read the question again. Use the Taylor series for f about x equals 1 to determine, okay, any points of inflection. So the second derivative, I need to know if it's positive or negative. Well, here's the thing. All the powers of the variable, the only part that could be negative is whenever I plug in here, right? So if I plug in x's that are negative, or I guess less than 1, then this is a negative value, but then you raise it to the second power, you raise it to the fourth power, you raise it to the 2n minus 2. So I would say that f double prime is positive for all x. Therefore, there are no POIs. And you have to imagine that it's an answer like this anyway, just because, I mean, how are you going to set this equal to 0 and solve for a 0? You know what I mean? It's an infinitely long polynomial. So, I think as far as that goes, you should expect, if given a question like that, that it's not something where you're just like, and it's going to be at 7. You know what I mean? And there we go. So, yep. Since every term in the series is non-negative, the second derivative is positive for all x. Therefore, the graph of f has no points of inflection. Okay? And there we go. And that is the end of the 2009 FRQs.